Hey everybody, so in this video, I'm going to go through a couple of examples working with group algebras, and I thought I'd try something different, a little bit more organic. This is just a notebook where I do calculations and think about things, and I thought it would be interesting to go through some of the questions without writing everything out properly. Like when I make these videos, I make a little script, and I do a couple of drafts, make sure everything is neat and tidy, but for these examples, I kind of wanted to just go through the questions as I was thinking them out and share with you my thought process as I work through the problems. I think that's a good way to go through problems because you need to learn how to think about problem solving, and I'm sure that you guys at this level have a lot of practice with this kind of stuff, but maybe I have something that I can share, and if nothing else you get to see the examples. Or you can just skip this video, you know? But so for this first example, our group is D8. The symmetries of a square. Here's a presentation of it. So we have two generators. One has order 4, one has order 2, and they obey this equation. This is going to be key for working with this group. So if we look at the group algebra for G over the complex numbers, C D8, and we take two guys from there, specifically A plus 2A squared, that's an element of our group algebra, B plus AB minus A squared, that's another element of our group algebra. We're going to do a couple calculations with these guys and just see how working with the group algebra behaves. These are the three guys we're going to compute. Groups are not necessarily abelian, so it stands to reason that when we have the group algebra, the multiplication within that group algebra may not commute. It probably won't. So here's a little example to look at that. So x times y, write these guys out. So this is me just multiplying it out. A times the first guy, just like in high school. 2a squared times the second guy. So I've expanded. Then here I simplify. So I made some computation errors, right? I'm just going through it as I go. Simplified a little bit. These little squiggles are just when I write it down on this line just to keep track of who I've carried over. And I just use simple properties of the group, like A4 is equal to the identity. Minus 2A4 becomes this minus 2E over here. I combine terms, right? We have the A squared B plus 2A squared B, that becomes a 3 over here. Just rearranged it, wrote it nicely. So nothing too crazy there. Then we have y times x squared. So if we write those guys out, we simply expand. A4 becomes E again. Now here I got a little bit stuck, right? Because we like to write our group elements with the A's followed by the B on the end. I mean, in principle this is done, but it's not nice and tidy. This is not as easy to work with. Oops, sorry, just kidding. So I did a little bit more simplifying. Brought these guys together. But I use that property of the group. If I multiply both sides of this with A, I get B inverse ABA, and this is just equal to E. And then I multiply both sides on the left with a B, then I get A BA is equal to B. Why am I doing this? I want this BA, I want to get this guy right here by itself, so I can know how to kind of turn these guys around. Like, how did I go from BA to A cubed B? Well, I can multiply both sides by A inverse, but what is A inverse? We know that that is just A cubed. So if we multiply on the left by A cubed, we get this guy, which is how we want it. We take the B's and we're able to move them over to the right, and I can just repeatedly use this to simplify as I need to get my B's over to the right-hand side of each individual term, and using that, I can simplify it down to our final result. So that was the trick. That was the thing I got stuck on for a second, but then I played around with it and was able to simplify these products. And the last product I looked at was just x squared. Well, this is nice because it's all A's, so I know that they're going to commute with themselves. So I can just multiply it out like normal, and I end up getting this result, right? Just expand and simplify. But since I know that they commute, I can just do like high school algebra. I factored out the A squared, and then it's the first guy squared, plus 2 times the second guy, plus the second guy squared, and then I just expanded this out and got this guy. Same answer, just playing around, nothing fancy. So for this guy, I have an element of my group algebra Z, and it's equal to B plus A squared B. Show that it commutes with all group elements in our group G, right? This is B, part B from the same question. So G is still D8. We're still working with C D8. And then once we have that, use that to show that Z commutes with all elements R, where R is in our group algebra. Now we know that all elements of the group are going to be in this form. We have powers of A that goes 0, 1, 2, 3, and we have powers of B that goes 0, 1. So my first thought was to just see how Z acted on a general group element, but that just got me really confused. So I thought, okay, let's look at the generators. Let's see what Z has to do with the generators, because I think I can construct something from there. And so if we multiply it with A on the right, I just wrote it out, I just expanded, then I used that identity that I found earlier. Remember, BA is equal to A cubed B, right? That's just from our presentation of the group. It's just a fact about D8. I was able to rearrange it, and I was indeed able to factor out A from this, which is just Z, once I rearrange it. So I found that A commutes with Z, so that's a start. And then I came over here and did the same thing with B. So if I expand it out, this is really simple, that's nice. I can take this and just multiply it by the identity, which I wrote in a clever way here as b times b, right? That's just the identity, it's its own inverse. If I send one of the b's back in, keep one over here. Well, this is just Z, this is B. I did find that B commutes with Z. So A commutes with Z, B commutes with Z. Like I was saying here, all group elements are just products of these. When I take Z and multiply it by any group element G, it's going to have a bunch of A's and B's. We can use the fact that it commutes with the two generators to pull them over one by one. And then we can actually extend that really easy to any element of the group algebra, because these are just linear combinations of group elements. And we know that Z being an element of the group algebra, we can pull out scalars. So again, term by term, we can do this product by product, and we have that Z commutes with any element of our group algebra. In some sense, it's a member of the center of our group algebra, whatever that means. My camera's dying. So compute the matrices for the regular representation of C2 by C2 over F. So we know that a group has elements that we can write out like these, but I've chosen to call them E, A, B, and then AB with a circle around it. I just made this up, but if you think about it within the structure of our group, this is just A plus B. So I just called it A plus B with a circle around it to show that it's one group element. Now for any element of our group algebra of F C2, C2, this is our group algebra, it's going to be written like this. We have our group elements as our basis vectors for our vector space. So now I'm looking at how the group elements act on our vectors, just like we saw in the examples in the last video, because if I know how they act, I can then pick a basis and turn them into matrices, which is exactly what I did. So I just wrote out the product, simplified, and then here I picked my basis. This is just a natural basis. I called that basis map fancy B. I'm not being super rigorous. These are just sort of my calculation notes, like I said earlier. If we write out our vector in this basis, we get these guys as our components, and we know that writing out this vector, A acting on S, remember that gives us back a vector, this guy is a vector, gives us this. So if we think about how these get rearranged, right? A acting on the first one, well, we want 1 to survive. So this is lambda 0, lambda 1 survives, makes it over here. Lambda 0 survives, makes it over here. Lambda 3, lambda 2. And then I figured it out for the other generator. For B, just wrote really quickly, when B acts on it, it acts like this. Follow the same process. We get the group action of B written in this basis, gives us this matrix. And because it's a homomorphism, we can just take products of these matrices as we need to be able to generate the matrix for any element in our group. So without actually taking these products, we've essentially solved the problem. Again, these are just notes that I do for myself when I'm making these videos. Just wanted to share the thought process with you. So let's see if I can squeeze in one more example before my camera dies. Consider CC2. So elements are going to look like this, right? There's only two elements in our vector space. Consider two guys, R and S, in our group algebra, CC2. Here are the two guys. These guys are all complex numbers. So the question is, if these two elements of our group algebra multiply together with our group algebra product, will it give us the zero vector in our group algebra? So if I multiply these two elements of our group algebra, right, this is our group algebra product, and get back the zero vector from our group algebra, does that imply that R equals 0 or S equals 0, that one of these is the zero vector? Well, if we write out R and S, we know how to multiply this out with our group algebra product. Expand and simplify. We end up getting these guys as our components for E and A. That's the product. Well, suppose that this is true. Suppose that we multiply them and we get 0. Then we have that this guy has to be the negative of this to give us 0, and this guy has to be the negative of this to give us 0. Right? This and that. We've got two equations and 4 unknowns, so I'm just going to let both of our lambdas be equal to 1. With that choice, that gives us these equations. Well, then I'm just going to make another choice and let mu e equal 1. If I do that, it says that mu a has to be minus 1. So that tells us that with this choice, we have r equals e plus a and s equals e minus a. Then if we multiply these guys out, it does indeed equal 0. So we know that the original statement is not true because we found a counter example. E plus a times e minus a in C2 multiplied together give us 0. So this is in fact false. Sweet, I made it without the camera dying. I like doing this video. Hopefully I'll be able to do some more example videos like this where I get to just show you my thought process and how I work through some problems. Maybe next time I'll do some proofy stuff as opposed to so much calculation stuff, but I think calculations are super illustrative. Sorry if I'm talking fast, I was afraid my camera was gonna die. And I'll see you guys in the next video. We are going to be talking about, looks like FG homomorphisms. That's some good important stuff. Okay, see you in the next video. Bye.